In this module, we are going to understand about Azure Databricks. And Azure Databricks build up on top of Spark. So let's see how Spark evolved over a period of time and why is Spark so famous in big data technologies ecosystem. Traditional enterprise systems used to have a centralized server to store and process the data. And this traditional model is certainly not suitable to process huge volume of scalable data because the centralized system creates too much of bottleneck while processing multiple files simultaneously. Google solved this bottleneck issue using an algorithm called MapReduce. MapReduce divides a task into small parts and assigns them to many computers. Later, the results are collected at one place and integrated to form the result dataset. Studies reveal that while MapReduce produced a good fit for a wide array of large-scale problems, but MapReduce lacks a data sharing abstraction for leveraging distributed memory. Such an abstraction would allow many applications to have concurrent data access to memory across the cluster. It also suffers from many performance problems due to its insufficient use of resources. Example, poor memory utilization because MapReduce used to spill the data to the disk after each job. Now, recently, one of the framework which are trying to address these problems, these issues, is called the Spark. Spark relies on a spatial abstraction and it's called a Resilience Distributed Dataset or RDD. And this support iterative, interactive, and streaming applications. Now we will discuss RDD in detail. But before that, let's first understand a very high-level overview of Spark framework. So as I said, Spark is very popular in the big data community. It is a open source, and this Apache Spark is an extremely fast, very powerful analytics engine for large-scale data processing. And it processes all kind of data. Maybe it's structured data or semi-structured data or unstructured data. It is an in-memory engine, which means that it does the data processing in memory, and it can run workload up to 100 times faster than Hadoop. Yes, you heard it right. 100 times faster than Hadoop. Basically, it has a very highly scalable architecture that allows to run on hundreds and thousands of machines together and process terabyte of data in parallel. And a Spark can also be used in a variety of use cases, whether you are processing the batch data or the streaming data, or maybe you're doing the machine learning or any kind of advanced analytics. Spark can be used almost in all kind of processing environment. Spark is a part of Hadoop ecosystem and it is built on top of Hadoop. So it makes sense that we spend at least some time to understand the basic components of Hadoop. Hadoop was one of the very early frameworks for distributed computing where the actual cluster nodes were made of off-the-shelf components. And this Hadoop software knew how to run processes on these components and get the result back to the user. And this Hadoop is made up of HDFS, which stands for Hadoop Distributed File System. A distributed file system which actually stores the data across multiple nodes. And this MapReduce framework within the Hadoop is responsible for data processing. And this MapReduce is actually that component within Hadoop that define what transformations we want to apply to this distributed data. And then we have Yarn component, which stands for yet another resource negotiator. And this is the framework, Yarn framework, which actually coordinate and run the data processing task. And here is how the typical life cycle would be for a task defined on Hadoop. As a user, you would define a map and reduce tasks using a map reduce API. These task binaries would then be fed into the Yarn cluster manager, triggering a job on the cluster. And then Yarn would take care of the resource allocation required to run this task, actually execute the task and store the result in HDFS. Now, this is relevant to Spark because the basic components that you will see in Spark are built on top of these Hadoop components, especially Yarn and HDFS. When you use Spark, instead of writing your processing task in the form of map and reduce operations, you will indeed use the library specified by Spark code. And this is the general purpose computing engine. Once the task has been defined, this will be run as a job by the cluster manager. Yarn can be your cluster manager. You can also plug in other cluster managers such as Apache Mesos. You may also use Spark standalone where it is operating on a single node. You will be running data under higher level APIs which provide many nice abstractions. However, the underlying data will still be stored on the HDFS distributed storage system. Built on top of the Spark code implementation, which deals with the distributed data processing, are many libraries that are useful, such as Spark SQL or streaming or machine learning library, MLlib, and GraphX. As the name implies, these libraries are geared towards specific use case for which you might need Spark. When Spark is essentially running on top of Hadoop, why is it that we actually need Spark? In my opinion, the main reason for Spark popularity is the abstractions that it provides for distributed processing. You work on data as though it were on a single node, but under the hood, the data processing occurs on multiple nodes on your Spark cluster. Spark also offers native support for many use cases where bare bones Hadoop does not suffice. Spark allows you to perform real-time as well as batch processing, and from Spark 2 onwards using the same APIs. Spark also has a very intuitive and easy to use REPL environment. REPL stands for Read, Evaluate, Print, Loop. This is the interactive shell which you can use to run and prototype Spark programs. You might be familiar with the interactive shell when you use and run Python. Spark offers libraries and support for a number of languages like Python or Java or Scala or R, and you can pick the programming language of your choice to munch the data. Now let's talk about RDD, which is the basic building block of Spark. Any developer, or in fact anyone, if you want to start with Spark, it is important to have a very good understanding of RDD. Because as I said, RDDs are the fundamental building blocks of Spark. All the APIs, data frames, data sets, or anything else are built on top of RDD. Now let's try to understand RDD in its most fundamental form. So RDD, you can see it just as a collection of any kind of entity. It can be a simple integer, or maybe a string, or objects, records, rules, or anything else, any entity. Now you may not have worked with Spark before, but even if you heard about Spark from any developer, you often might have heard this say that Spark is very fast to use. And this is because all the operations in Spark are performed on in-memory objects. You're not going to back to retrieve stuff from the file system from HDFS. This is very significant difference between how Spark operates and how Hadoop works. These in-memory objects, which we use for data processing, are called RDD, or Resilient Distributed Datasets. So as I said, RDD can be of any entity, and these entities processed in memory by Spark. Now let's move forward. There are two types of methods in RDD anyone can do. So the first one can change the content of an RDD and produce an entirely new RDD or collection. And second one can return the contents of the RDD, maybe in the form of printing to the screen or maybe writing to the file or something else. So there are two methods. First method can transform the RDD, can make changes to the RDD. And the second method simply return the value of the RDD. That's it. Even though we have defined RDD as a collections, they are actually special in several different ways. And here are three characteristics of RDD which make them different from ordinary collections. The first of these is the fact that RDDs are not collections on a single machine. RDDs are partitioned. The entire contents of an RDD are split across multiple nodes in your Spark cluster. RDDs are also immutable. Once the RDD has been created, they cannot be edited or changed. All you can do is apply some operation to it to create a new RDD. RDDs are also resilient to node failures. If a node which holds an RDD crashes, that RDD can be reconstructed from its raw form. So this RDD is basically a collection, and different subsets of this collection are distributed across multiple nodes in your Spark cluster. This allows operations to process the data on these nodes in parallel. This distribution of RDDs is completely abstracted away from you as a developer. So for you, you will be working on one cluster, but behind the scene, this data will be distributed in multiple nodes. Every RDD entity is a row in this tabular format. The most important thing about Spark is that the contents of this RDD are kept entirely in memory across multiple cluster nodes. The RDD that you see depicted in a very basic fashion on a screen is literally separated into partitions and spread through several machines. So the data doesn't look like a single table. It partitions into multiple parts and spread across the cluster. But all you need to know as a developer is that this is an RDD. You're going to treat it like a single collection. But without your knowledge, under the hood, the contents of the collection are distributed or split across multiple machines. These devices are nodes of your Spark network. So they can be real machines of your data center or virtual machines in the cloud. The main reason for the splitting of data across multiple nodes is parallelization. Data can be processed in parallel on all of these individual nodes. Parallel operations on data is an essential prerequisite for big data processing. Otherwise, it's impossible to process terabytes or petabytes of data in a matter of hours. Remember, in Spark, all of this data is stored in memory for every node in the cluster, not on disk. Now, the RDD once created cannot be edited in any manner. Individual entities cannot be updated, and the RDD cannot be added to or removed from. And there are only two operations that are permitted on an RDD. All the RDDs can be transformed. Transformation involves extracting or changing the contents of an RDD to construct an entirely new RDD. You can also perform actions on an RDD. An action is any method which requests a result from the RDD. Tell me the result of all the operations that have been performed, printed to screen, or written to file. All of those are actions. Let's look at the transformation first. Typically, you load a data set and create an RDD in your Spark program, and then define a chain of transformations on that data set to basically set up the data set the way you want it to look. So, for example, you might want to load all the data into an RDD, pick only the information in the third column. Maybe you sort those values. So all these are examples of a chain of transformations. And when you apply transformations on RDDs, you will find that they go really quickly. That's because when you apply a transformation, it's not actually executed. The actual execution of individual transformations is done only when you request a result. So that is an action. You might want to see the first 10 rows of your data to see what they look like. That is an action. You might want to get a count of a rows. That is an action as well. Or you might want to calculate a sum. All of these are actions which cause the RDDs to apply the transformations. RDDs perform what's called lazy evaluation, evaluating the data only when an answer is specifically requested. All the transformations on the dataset are set up as a direct acyclic graph. The nodes in the graph are the actual operations performed on the data. And then, when an action is requested, Spark can efficiently compute the best possible way to process the data, execute operations in parallel, and return the result to the user. Now, let's summarize this. So the RDDs are immutable. They support only two kinds of operation. The first is an action where you actually read the contents of the RDD and maybe print to the screen, or maybe write to the file or something else. Or the second is maybe you want to transform the content of an RDD, perform some kind of operation on every entity, and create a new RDD with new entities. So we now know why RDDs are considered distributed collections. Let's see why they are resilient. This is because RDDs can be reconstructed even if the node that hosts this RDD crashes or fails. So in order to understand what makes RDD reconstruction possible in Spark, let's step back and understand the two ways in which RDDs can be created. You can read a file in and the contents will be stored as an RDD. Or you can apply a transformation to an already existing RDD and generate a new RDD from it. However, the point is every RDD keeps track of where it is coming from, the file source or another RDD. As you perform a series of operations on RDDs, this is the chain of transformations. Each one of these transformations is tracked by Spark. However, many transformations led to the current form of the RDD. All of these are tracked in metadata, and this is called the lineage of an RDD. Every RDD in Spark is aware of its own lineage back to the original source of the data. And it is this awareness of lineage that allows RDDs to be reconstructed when the nodes crashes. The metadata can be used to figure out where the RDD came from and the series of transformations which produced it. Lineage also allows lazy installation or lazy materialization of RDDs. When you access the results, this lineage is used to figure out all the transformations that have to be applied until the final result can be obtained. And please remember that you might never encounter the RDD as a construct when you work with Spark 2. However, remember this forms the basic building block of any data structure that you use, whether it's a dataset or data frame. So for all the Spark version 1, the data structure that you would work with directly when you are writing Spark programs would be the